So at this point, we have studied the LLT method, VLM methods we have seen, and also 3D panel methods. Okay, so we have covered 2D and 3D. So now we're going to study CFD, computational fluid dynamics. Okay, that probably is the most accurate of all the previous methods. Okay, between all methods is the most accurate, but it is very expensive and requires some user experience. So I'm going to show you how to run a simple case. Okay, I will ask you to take the same profile that you took in that you use in Xfiles, and let's simulate it here. So you are going to get a feeling of this next step. Okay, and you will see that it requires some knowledge and a lot of work. Okay. So here we have the methods from, let's say, computational complexity and computational overhead. So these methods they are not very expensive, but then we go in CFD. Okay, they are very expensive. We are solving the real equations. Okay, the Navier-Stokes equation here. We're solving now those simplifications. Okay, so we're moving now in CFD from those sources, doublets, vortex filaments, horseshoes, vortices, panels, and so on. We're moving just to solving the actual physics. Okay, we have these Navier-Stokes equations, okay, that predict very well the fluid dynamics. Okay, and we're using numerical methods to approximate the solution. Okay, these solutions, these equations, the Navier-Stokes equation, they look difficult and they are difficult. They are hard to solve. Okay. So thanks to the numerical development of numerical methods and computer hardware and the use of CFD solvers, we can get very good solutions. We're going to use Fluent, okay, which is one of the many solutions that are available. But basically, the idea in CFD is that you need to subdivide your domain in many control volumes, you see here. Okay, so previously we haven't done this. Okay, and if we have done something like this at the surface level, okay, but we don't know what is going on in the domain. Okay, so here you need to subdivide this in many small pieces and control elements, okay, control volumes, and in each one you are going to find the solution. So it's clear that the more elements that you add, the more accurate, or we hope the more accurate the solution will be. Not necessarily. Okay, there are many factors influencing that, but see here that we have this nice airplane, and see that we have a very fine mesh close to the body. We need to resolve well the curvature. Here you can see, but you have the boundary layer. You need to resolve also boundary layer. See that also we have a refinement zone, okay, to resolve better now the vertical structures here close to the body, vortices, and so on. So this requires some manual work at the time of doing the mesh. This is called the mesh. So the equations that we're solving are these. Okay, so these are the equations of fluid dynamics. Okay, so we're talking about aerodynamics. Okay. So Navier-Stokes equations are able to predict very well the behavior of fluids. Okay. As you see here, they look difficult, and they are difficult, as I mentioned, but not only we have this set of equations, plus this one we have many closure models. Okay, so those things that we cannot resolve directly with this, we resolve it using models. So the most well-known models is turbulence model, and this have an incredible effect in your final solution, and it's very important to take it into account. So behind this one there is another theory. There are many turbulence models. So I'm going to give you a faster recipe how to get your geometry, do a mesh, and then how to select or use turbulence modeling. But later there is another course that we will go in details about turbulence modeling. Besides this one, you can have chemical reaction, combustion, acoustic, multi-species, particle interaction, Lagrangian particle, mass change, mass transfer. Okay, you can have also coupling with magnetohydrodynamics, with electrical fields, potential fields, okay, and structural dynamics. So it's very complex. Okay, plus having everything here, equation, models, you need to define also boundary conditions and initial conditions. So you need to say what is entering, what is going on, what is going out, what is going on in the domain, at the walls, is your initial condition that previously in the previous methods that we have used so far, we haven't done that. So as you see, things get very complicated. I already mentioned this one, but CFD, remember that CFD is too expensive to be used during the preliminary design phase, okay? But if you don't have any other choice, okay, you can go ahead and use it. But you will see that in the time that it will take us to do one simple airfoil, probably you will do thousands of simulations using airfoils, also thousands of simulations using the LLT method or panel method or vortex lattice methods. You have done optimization, you have done a very good design. Instead, is you take CFD all the time that you just take it to do one case, it will be equivalent to running thousands of simulations using the previous method. Here, finally, just I'm comparing here now the previous case that we have worked so far, now the 3D wind I have shown you. And here we are comparing the three methods. So we have the experimental results, another reference results, and then we have the LLT method, and then we have the CFD. So you recall, I hope you recall that to get this solution using the LLT, okay, it's very fast. Okay, it takes it's just a matter of pressing enter, and you get the values, and you get a very good prediction. And these green dots here represent the CFD solution. So here, just you can imagine to generate this green dot is something that can take hours doing geometry, doing mesh, and running the simulation. So in those hours, you are running, as I say, thousands of simulations using the other methods, and you see that you have the very good agreement. The advantage of CFD, as you will see, that you are going to have an instantaneous snapshot. Okay, can be in time or iterative margin, okay, of what is going on. You can see how the flow is evolving all around your domain, okay? Something that you cannot get using the potential methods, and also something that you do in experiments is very difficult to get, okay? You cannot go enter and into your geometry and measure all around. Here in CFD, you can do everything. And something that I will address also briefly, but later when we address the proper turbulence in another course, we're going to talk about assessing convergence, because also previously you have seen that convergence, we haven't looked at that. There is no need to look at that. Those methods converge very fast. Okay, so there is no need to look at that. But see here that depending on your flow is that you have attached flow or separated flow, you can have oscillations in the quantities that you are monitoring. So see that here we're monitoring the lift coefficient, and see here that at 14 degrees as we expect, we have flow separation, and see that you have your coefficients oscillating. So the question is, when do I stop? Can I stop here, 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 or I let it run 5,000 and then average the solution? So there are many practical aspects that you need to know, and you will get experience now while doing. Okay, so it is not easy. CFD requires some experience. Okay, so we're going to give you just a brief introduction in Ansys Fluent, okay, to do CFD. So the first thing is that I will show you fast a case. Okay, so go and find your Ansys installation. In my case, I have it here, and to launch Ansys, you go here down, and you will find this Workbench 2020. Okay, so this is what you need to open. So later I will send you some files, okay, with some solutions. But you open that one, and you are going to get the Workbench. Okay, so this is an integration of all tools that you have with Ansys. Okay, so takes some time to open. Don't worry about that. By the way, also we're going to run small cases, okay? So they should run in any computer, so you don't need to have a very good hardware. So you're going to get this window. So here you have all the applications that comes with Ansys. So we're focusing CFD here. You have also structural dynamics, a lot of stuff you have here inside, okay? But we want to focus in CFD. So the workflow in CFD is that generate a geometry, do a mesh, and then pass to the solver. So just to show you how things work, here is drag and drop, okay? So you choose, you identify what you want to do. So see here that you have the geometry model. drag and drop there. So here you do the geometry, then you are going to do the mesh. See here that you have mesh model and you put it here. So you connect the mesh to the geometry, and then you have a mesh and you select your solver. Okay, so you have different solvers, by the way. So in this case, we're going to use this Fluent, and then you drop it here. So this is how you work. And then you can also do different cases. So you see that you can create parametric studies, so you can have two Fluent cases, and each one with different boundary conditions. You can have different geometries. So this is very handy, okay? So you can also delete here. So you just need to play a right click, left click. So this is how we work, okay? So I'm going to show you a workflow of one case that I already have done here. So you will see how things are done. So here I have it. And I will open this. So this is a case of an airfoil. So see that here I put different cases. So here I have a geometry mesh, here geometry mesh plus Fluent solution. So see here, pay attention when you see the check mark, means that you have a valid geometry, a valid mesh, or a valid solution. When you have something else, it means that you need to be careful. So see that if I put something here, question mark means that you don't have anything. So you need to enter there and do it. So just to enter there, just right click. And then you have here the different options to choose. In this case, the geometry modeler. So we're going to use design modeler, but for the moment, don't open it. So I want to show you all the steps here, and you will see that it's very time consuming. So I will open my geometry. I use the design modeler. So as I mentioned, this Workbench is an integration of many programs. Okay, so we connect the design modeler to a meshing tool. So in this case, we're doing a 2D geometry. So see that this is for those who has a good eye, this is a NACA 0012, okay, symmetric airfoil. But see the steps that you need to import this geometry. So you know how to generate it, you can generate. So what we need here are the coordinates, okay? So you get the airfoil coordinate. By the way, the format, how you get it is very specific. We're going to address this one, but just to give you a preview, that it needs to be something like this. It's a file, something like this, and it needs to be divided like this. So here you have groups. You can read in different curve, okay? So in Ansys, you can have a closed loop with a single curve. So in this case, see that we have an airfoil, but this airfoil is not a closed loop. It is divided into geometry. So see that here we have upper and lower surface. So you can get that from your geometry, and you need to split it, okay? Upper and lower surface. Okay, so here I rotate it as well. So you read the geometry, the format will give you this later, but this is how you read it, but very straightforward, okay? So here's 3D, you have also the search component. In this case, I'm giving you something general, but for us here, you will have coordinate, X, Y, and Z. So, having said that, we can move here and see that here, import coordinates. See that I'm reading a coordinate file. Then from those coordinates, I'm creating a surface, which is the airfoil. So let me go here, and so see that here we have the airfoil. So I'll suppress. So see that I'm reading in the airfoil. The next step is this one. From those curves, and something important here, we need to work with surfaces and volumes. So in 2D, I'm using a surface. I create a surface using that curve. Now that I have that surface, I create my external domain. So see that I create my external domain. So later I'm going to give you some guidelines to let you know how big should this external domain, that box, be. Then here I can do this, adding some modification just to have the case parametric. Okay, so I want to run at 3, 4, 5 angle of attack, so I don't need to redo everything. I just add the rotation here, and then everything is done automatically. Then I do a Boolean operation here. So a Boolean, let me suppress this one just not to create. So a Boolean consists that the surface, the airfoil surface, subtract that to the outer box. Okay, so now you have a hole. See that you have a hole. Okay, so you have a hole there, and now this is a valid geometry, but I go a step forward and I will add around this body another box where I want to refine the mesh, okay, because I know I have a wake. So see that I create this second domain. So this needs to be different geometries, okay. So you go here, okay, this later I'm going to details that needs to be suppressed, and you have a valid geometry, okay. So this is your airfoil and this is a refinement box. Then you go to the mesh. Okay, so in the mesh, you are going to take that geometry. This is another tool. Okay, you have it here, mesh, put it there. And you're reading that in. So it takes some time to read sense. So now that you have attention, these are warning, okay? So it's just warning, don't pay attention, or probably pay attention, but it is okay to go. If you have an error, you need to correct it. So here you have your geometry, and then you can generate the mesh. So these are parameters to control. Later I will explain you how to do that, but let me generate this mesh, okay? And this also requires a lot of experience. So now you might guess that everything that we have done, this is here I'm showing you this test fast, but this is something that can be 1-2 hours. In 1-2 hours, you can do a lot of potential simulations that are very reliable. So see here that we adding close to the body these prismatic layers to resolve the boundary layer. Remember, a boundary layer is very thin, so probably we might not be resolving the boundary layer. We're using models, okay, to capture what is going on there. But what is important when you do the mesh, you need to resolve the curvature, and also the elements close to the body needs to be small enough so it also captures the vertical structure, so the structures that are developing close to the body. And then see here that we added that external box to put more cells here to resolve the vorticity or whatever you have there, okay. Then also you need to add boundary conditions. So see here that you have different lines or surfaces. So initial this one, you need to add a boundary condition. So probably these two, this is the airfoil, those are walls, this is the inlet. So far also using the potential method, we haven't defined boundary conditions. This is part of the CFD. You need to give boundary conditions, initial conditions. You have an outlet and you have a button, and then you need to give your setup. So we have a valid mesh, and then we can move to the next step, which is solutions. Okay, so you have the mesh, you convert it, you put your solver there, so this will take a few steps, and now you double click there. Okay, so you drag your solver into the mesh, you double click there, and you are ready to go. So let me launch here. Okay, by the way, also you can close this one, you need to leave it open. Okay, so we have fluency. This is a warning. Again, don't pay attention. You see the BKI stuff, so warning. So it is reading the mesh that you created. Okay, it knows that it's a 2D mesh, and see here that you have the mesh, and now since here it gets complicated. So if you think that airfoil was complicated or XFLR5 was complicated, look at all these actions. These are things that you need to control in CFD. Okay, so we're going to address this one. I'm going to give you the recipe now to do this. Okay, but basically in this case, we're going to run, this is at 0 degrees with some values, so you are going to choose models. So here see that you choose turbulence, multi-phase, energies, you have compressible flow. Okay, so this is not a correction that we have done so far. This is the actual energy equation, and you're computing density values, everything. Then you can choose material models for those materials, ideal gas, whatever. Here you have boundary conditions. So here, this is an inlet. So see here that you need to say now, okay, it is entered with this velocity. So if you want to run with a Reynolds of 3 millions, you need to compute your velocity, or you need to change viscosity, whatever you choose. But here it's not like previously that sometimes we don't give anything. You have a full implicit solution, you don't care, you don't give anything, you get your 2 pi for this lift curve. But here you need to give value velocity. Okay, this this viscous solution, okay, the outlet, and see how complicated it is, okay. So then you give options. These are for reference values to compute coefficients if you want to compute coefficients. Then you choose the method. You have many methods available to solve the equation. Just to show you, there 4 different methods, okay, they have there, and then you have different options, okay. And same here, more options to control. Then reports, here you set up reports to compute coefficients. So in this case, we're computing the lift coefficient in this surface. So remember, when you create the geometry, you gave it this name, so you access those names there, and so on. So then to run, you need to initialize, you need initial conditions, okay, and now you are ready to go. So you press here, calculate, and it will start to run. So see that is monitoring, it's giving you information of CL, CD, and then the residuals. So I'm going to address this fast, but this is also create a lot of confusion because people want the residuals to get, I know, 10 to the minus 4, because that means converge solution. And that is, I have to say, that is partially true. It's not totally true, but it's partially true. But if you have a fully on a steady flow, these residuals will never go down, okay, will stay up. So what is important when you look at the residuals is that they shouldn't go up, or they shouldn't be more than 1, okay. But what is important is just to monitor a quantity of interest, okay, integral quantity. And see here that you have CL and CD, and see that it's not oscillating. This is a good indication. This means that probably you have arrived to a converged solution. See that CL, as expected, should be something about 0. See here that it's getting to that value. Then you have CD0 is this one. So here now you have everything, okay. You have all the viscous effect, everything there. As you go to 3D, also you are going to have your skin friction plus induced drag, everything. And if you want to do the decomposition, it's a little bit more trickier, but you are getting here the actual forces, everything. Okay, so see that here. I will let it iterate a little bit more, because it should converge, it should stop. But okay, see, it's not going down, it is oscillating. So let me stop it here, okay. So see, these are things that you will encounter, that probably your residuals remains stalled. That is not a bad indication, that is actually nothing. And then you can just plot, for instance, you can see the colors. And now here we have access to the whole fields. So see that now you start to see colors. It's a symmetric solution as we were expecting. So this is a pressure field. You can have also velocity. Okay, so this is the velocity, and as you go in, see that now you are resolving boundary layer. Okay, so for the turbulence model that we are using, okay, we are computing something. Okay, so we have the fully turbulent boundary layer. We can also model transition, like what is done in Xfull. In CFD, transition is very expensive, but later in the turbulence course you're going to see that. You can also plot, for instance, CP distribution. So as you go here and I select this pressure distribution, so you have airfoil bottom and top, and this is why it's also a good idea to split your geometry into parts, okay, because you can plot in different components, you can plot everything, okay. So if I plot velocity, this is boundary layer, so it should be 0. So this is the steps to run a CFD solution. Then also you have reports here. So for instance, you can compute integral forces. So you have access to everything. So for instance, you want to get your forces. See here that you have your forces in Newton or the coefficient. As I look lift, remember lift and drag are parallel and perpendicular to your incoming velocity. You have your lift force on something that is about 0, okay? So this is the workflow of that CFD simulation. As you have seen, it's not easy, it's not straightforward. However, I'm going to give you the recipe, okay, to run a simulation of an airfoil, okay, and then you are going to choose the same airfoil that you use in Xfull, and then we're going to compare. So don't worry, the simulations are fast, okay, it shouldn't be more than 10 minutes. So let's say that probably in one day you can set up everything, okay, so you follow my guidelines. So this is the introduction. In the next video we're going to go step by step to set up the case. So thank you for your attention. See you next time. Bye.